Right, residue curves. So what I'm looking for from you in this section is how to use residue curves to be able to create a new separation process. So residue curves are especially useful when it's not zeotropic distillation, but azeotropic distillation. Zeotropic means ordinary distillation columns, and ordinary distillation columns we've adequately covered in the last few lectures, where we could use heuristics and we could use the Tedder and Rudd method. There were several different ways of sequencing ordinary distillation columns. When you've got azeotropic distillation, that's when residue curves become really useful. So let's start off by looking at what is a residue curve. If you've got an organic liquid with several components in a still, you add heat, some of those organic compounds are going to evaporate, are going to boil off, and we want to talk about a differential amount of vapor that comes off as soon as you heat this mixture. And the Xi is the liquid composition, the Yi is the vapor composition, and as long as there's a difference in the relative volatility of the different species, then the composition of Y is different to the composition of X. And that's normal mass transfer, vapor-liquid equilibrium theory. I don't want to go into derivations, but essentially what we're saying is we want to look at a differential amount of Y leaving, and we want to have a look at what is the composition of the liquid that remains, the residue. So remember that in the following few slides, it's always going to be the residue, the composition of the residue. Oh, wait. I've forgotten pointer. Residue. It's the composition of the residue that's important when we look at residue curves. So as we evaporate liquid from this system, the composition of the liquid will change, and that will follow a residue curve. Okay, so let's move on to the next slide. So we've still got this this container that we're going to heat, and we're going to evaporate some of the liquid. So let me start using these tools, and we're going to put an X in here. That's blue. Wait, let me clear first. Clear that one. And now we can use red. X marks the spot. Okay. So let's say we've got A, B, C, where A is the most volatile, C is the least volatile, and we can plot the composition of that liquid on a turn plot, where X marks the spot. And there I could use the pointer to show that that's where X marks the spot. Now, as we start boiling off liquid from that residue, in which direction will the liquid composition move? Okay, it's going to move generally away from the lightest component, and it's going to be moving towards the least volatile component. So let's just put in an arrow. What have I got at the moment? Pencil. Yeah. So if we go this way, it will be a vector. The movement of that away from point as we remove vapor from the liquid composition will move, and it will move in a certain direction. In other words, there'll be a vector on this diagram. And in a similar way, if we start with a liquid composition that looks like that, it will also have a vector, and we can start putting vectors like that all over this page. Whoops, that's a straight line, guys. And anything that's close to A will have a vector that moves directly away from A. And anything that's over here that's got lots of B in it will move towards C and away from A. And now let's look at if we've got a binary mixture. If we've got A and C only in that liquid, it's clearly going to move away from A. Oops, that's an arrow. There we go, arrow. It will move away from A. So if you've got a composition over here, it's going to be moving towards C. If you've got a binary mixture that is A and B, it will move away from A and towards B. If you've got a binary mixture of B and C, B is more volatile than B is more volatile than C. So the residue will tend towards C. Right. And it doesn't matter how much A, how much C. If we're looking at this line over here, it doesn't matter how much A and how much C there is. It will always be moving downwards. The residue will always be moving downwards and eventually land up at C. Anywhere along this line, the arrow will definitely go towards B. Everywhere along this line. Similarly, everywhere along this line. It will go from B towards C. And so what you can see is we will eventually have a whole host of lines. The ones on the axes are already pointed out, but we're going to have a whole host of lines that satisfy all the vectors we've drawn in. Oops, that line is going. Okay, these lines never cross the axes. And we might have a line that runs over here. And we might have a line that runs over there. And a line that runs over there. So this is a zeotropic system. In other words, if we've got ordinary components that can be distilled with ordinary distillation, A, B, C, then you will get something that looks, you would get a diagram that looks something like this, except that these lines never cross. My mouse skills are not up to scratch here. And of course, the axis is a residue curve, and that's also a residue curve, and residue curves will never cross each other. So that was just a mistake that I made. If you have a look at this diagram as a whole, it's possible to cover the entire triangle with a series of lines that never cross each other. So when I give you these examples in tests and exams, all I give you is this order of volatility, or I ask you to work out what is the order of volatility from vapor pressure data. And you should be able to derive, knowing that there are no azeotropes, you'll be able to derive what the shape of these curves are, because there's only one way of drawing in an infinite number of curves that don't cross each other. And the way that you'll do that is to have a look at the axes first, A down to C. You'll be able to draw in that arrow. From A to B, you'll be able to draw in that arrow. From B to C, that arrow. And from there, a line that's running parallel to this one can only run in one direction. And ultimately, it must land up at the least volatile component. Okay, so now we're starting to get two things. There's a stable, what do we call it? It's a stable point where C is a stable component or point on the graph, where all of the residue curves run towards. Node, stable node. Thank you. Thank you. I needed that. Okay, and then there's this is an unstable node because all of the residue curves will move away from that node. Okay, so those two are represented by the unstable node by the least volatile component. Getting its phone call. So the least volatile component, or the most volatile component, will be the unstable node, and the least volatile component will be the stable node. And you'll see that the lines never actually reach B. And so this is called a saddle point, because it's only the lines that run along here that actually reach point B. So it's only the binary AB that will actually reach B. And then if you've got a tiny amount of B, a tiny amount of A in B, eventually of C in B, when you've eventually evaporated everything, that there will be an even tinier amount of C left. Okay, so that is a saddle point where B is, unstable node where A is, stable node where C is. Okay, I think we can move on. Is that all I wanted to explain on this graph? Okay, we'll have another more beautiful graph later. Right, so here, nitrogen, argon, and oxygen. Argon has got a boiling point somewhere between nitrogen and oxygen. So this is important for the separation of air. And that's a zeotropic system. In other words, there's no azeotropes in that system. So this is exactly what we've been talking about. Nitrogen, argon, oxygen. And if we now move to the right, we've got the same system. By the way, such a ternary diagram can be an equilateral triangle like that, or you can use an ordinate system, and you will still have the lever rule apply. So the lever rule, in other words, a mass balance, that you can draw a line across here, and if you've got something that's halfway across the line and you distill it, you can get something over there and you can get something over there, and it all occurs in a straight line. And similarly, that straight line occurs on this orthogonal system axis that we've got over here with H, L, and I. All right, so again, here is the saddle shown, where you don't have any residue curves actually touch. They will never actually go and converge on a saddle. Stable node. This one is this is the least volatile. H is the least volatile in this case, and that's a stable node. All of the arrows are going towards it, and here we have an azeotrope somewhere between H and L, which we mark A, and that is the most volatile component. So remember I said that low boiling azeotropes are the most common. In this case, A is an azeotrope of H and L, and it is the most volatile species, as if you consider it as a species, because it's when you've got the right combination of H and L, that has the most volatile composition. And that is the unstable node. So you'll note that there's an arrow pointing downwards from A down to L. Now L becomes a saddle because these residue curves cannot touch L. I is a saddle. This residue curve never actually touches L, and eventually H, stable mode. That's the least volatile component in the system of LIH. Okay, so again, I can ask you in tests. I don't give you a ternary diagram at all. All I say is we've got a ternary system. H is the least volatile. L is the most volatile of the pure species. I is in between. But I tell you, H and L form an azeotrope at 90% L, and that azeotrope has got a boiling point of, let's call this azeotrope a boiling point of 75. L has got a boiling point of 80. H has got a boiling point of 100. Then you know that that is a low boiling azeotrope, and therefore all the arrows will move away from it. In other words, A has got a higher volatility than L has. Right, so that's saddles, stable nodes, what azeotropes look like on a ternary diagram. So how does this help us? Well, firstly, we must recognize that the residue curves are actually an indication of the vapor-liquid equilibrium. And residue curves are liquid compositions at total reflux. So again, I don't want to go into derivations, but again, those vectors that represent the residue curves are simply a representation of the vapor-liquid equilibrium that we see. Okay, now we get to some interesting stuff. If we've got a, let's start. If we've got a feed that has got a composition over there, we know that we can have, I'm going to just get the line tool, that we can, with that feed and and we put it into a distillation column, that distillation column can make pure A. And on the other side of the distillation column, we're going to have a BC mixture. If we operate the distillation column in such a way that we have pure A, then by the mass balance and the lever arm rule, we would have something like BC on the other side of the distillation column. We could also operate, remember, C is the least volatile. We can also operate that distillation column by making pure C, and then at the top of the distillation column in the distillate, we're going to have A and B as a mixture. So this red line is a mass balance. Because it's in a straight line, it's a mass balance, and it says if we want pure A, then we're going to have BC at the bottoms. In other words, this red line represents a direct sequence. We're going to take off A first, and then we will have BC coming off at the bottom of that distillation column. Wait, pointer BC at the bottom of the distillation column. We can also operate the distillation column that we take off the bottoms first. If we take off pure C, that feed, we're going to have AB with that composition at the top of the distillation column. Now, there are other possibilities, and I'm going to change color. Where's my color? Color. First, I've got to choose a line tool, and we choose a different color. Purple. Okay, so let me draw a different line, and that is a line that starts over here and ends over there. Oops. Sorry, I'm just struggling with this tool. Okay, so you can see the purple line now. And I started it over here. I tried to start it. In fact, I started it correctly on this black line. And then I meant to end it directly on the same black line. Okay, so it's a bit short, but assume it ends on that line. It goes through the feed. That means if we choose a composition at the top of the distillation column, at the distillate of the distillation column, where I'm pointing, by the mass balance, the other side of the distillation column must occur somewhere along this line. And the vapor-liquid equilibrium of the residue curve says it lies on the same line, on this same line. So here I'm following this line until it eventually crosses the straight line on the other side of the feed. So that would be a possible distillation column, that we have a feed over here, we make a distillate with that composition. So that's not pure A or pure B, not pure, there are no pure components, it's a mixture of A, B, and C. And on the other side of the distillation column, we would have the same sort of composition. A different composition, very little A, and a mixture of B and C. Yeah, Jakelui.
So can we only end up with compositions on the same residue curve?
Yes. That line that goes through the feed, you can choose whichever residue curve you like. But if you've chosen it on this side, the other composition is going to lie on the other side.
Okay.
Okay, so I'm going to redraw that line, and I'm going to draw it on the axis. Oh, gee, that's not the type of thing. And if I do clear, I'm going to remove everything. Okay, I meant to do a line, not a pencil. Line. So here I'm going to start on the AB axis, and I'm going to end on the BC axis. Okay, can you see that? I'm going to get the pointer. So I've started it on AB, and we can follow this residue curve. The axis is a residue curve, and we can go around that sharp corner and eventually land up over here. That composition of BC will represent the correct mass balance for that feed, that composition, and that composition. And the vapor-liquid equilibrium is that we followed this axis for the vapor-liquid equilibrium. And so this is the only possible bottoms composition for that feed if the distillate composition looks like that. So now we start seeing that we could start with that feed. We could have a distillation column that has a distillate composition that looks like that. We can go through the feed, and we can have a bottoms composition that looks like that, because we would still be crossing this residue curve. So if we started there, straight line through the feed, on the other side of the feed where we cross the same residue curve, we've got both the mass balance correct because of the straight line and the lever arm rule, and we've got the vapor liquid equilibrium right because we are following the same residue curve. And now we can go and check. So that worked if we started over there. Now I'm going to change color again. First choose line and choose a different color. Orange, gray. Choose gray. Now instead of starting over here somewhere, let's try starting there. So now I'm going to draw the line. If we start over there, we take a straight line through the feed, and now you can see the gray line we started with, and get the pointer again. We started over here. The mass balance says we must go through the feed, and the bottoms composition will be somewhere on the other side of this line. Now, we've got to find where this line crosses the same residue curve. And the line doesn't cross that same residue curve on the other side. So that's just not going to work. If we work in the other direction and we start over here, over there, and we go through the feed, and we go through the feed, we can't cross that same residue curve again on the other side. So this is not a possible region. If we take somewhere along this curve over here, there, or no, we can take this one where the purple is. If we take that point, we go through the feed. Can we cross that same residue curve? Yes, we can, over there. So that is a possible, this purple line represents a possible distillation column. This gray line is impossible. You can't get a distillation column that operates on that gray line. Now, I'm going to erase everything again. And I'm going to go back to red line, go back to red, and I'm going to draw in a line that, well, a line that starts at A, goes through the feed, and goes onto that thing, down to the axis over there. And similarly, as we had before, starting at C. Can you see while I'm drawing this, while I'm drawing the line, or do you only see the line when I'm finished?
Only when you finish, sir.
Oh, okay. All right, there it is. It'll just help me to explain better. Now, we found that if we have a bottoms composition, well, let me get the pointer again. If we have a bottoms composition there, and the straight line has to go through the feed and then touch that same residue curve on the other side, that this is an impossible bottoms composition, because we can't touch that same residue curve on the other side of the feed. And only when we go on the other side of this line, somewhere over here, let's call it that point, we can go through the feed and we can touch that same residue curve up here somewhere. This is the residue curve that we've crossed. We can start there and we can end up there. So everything that is this side in this area is a possible distillation composition if we have this feed. We can make a distillate composition. We can design a distillation column to have a distillate composition that anywhere in this area. Because anywhere in this area, you can use a straight line through the feed and cross the same distillation residue curve on the other side. Okay, so I'm going to get my pencil, and I'm going to start marking in, shading in this area. So that area is the possible distillation, what you call it, residue, possible residue compositions that you can get using that feed. Similarly, let's go and look on the other side. We expect the distillate compositions to be on the other side of this residue curve that I'm pointing at here, the one that goes through the feed. We expect everything over here. Let's take this point over here. You can go through the feed and you can touch that same distillation, the same residue curve on this side as well. So we're expecting this area, and I'm going to now color it in with the pencil. This area represents the possible distillate compositions that you can get using that feed. just to prove the point, if we take well, if we take that distillation curve here, that distillation curve there where it crosses the red line, in other words, we're over there on that side of the red line, and that would represent any of the distillation curves, the residue curves that run along here. They're on this side of the residue curve, of the red line, sorry, like this residue curve is. If we take it through the feed, we can never cross that same residue curve again. And that's why that's why this red line over here is not the boundary, but the residue curve itself is the boundary. And the other boundary is the axis. Okay, let's have a look at this. This is a boundary. If we take a distillate that lies over there, and we go through the feed with a straight line, we can never cross that same one again, because now we're landing up with AC as the other side of the distillation column. And remember, A is the most volatile, C is the least volatile, so that's clearly an impossible distillation column that you can get. But the fact that you can see that on the residue curves, because if you choose that as the residue, straight line through the feed, you can never cross that same distillation column on the other side. Right, let's pause there and ask 4 questions. There's something that's not clear. Are you all stunned? So this is the way it will always be, that you'll take a straight line from the most volatile component, and if that most volatile component happens to be an azeotrope, you'll take it from that azeotrope through the feed, and you will only start drawing your line on the other side of the feed. And that represents the edge of this area where you can have possible bottoms compositions. Then you take your line from the most volatile component through the feed, and you only start drawing your line on the other side of the feed. That represents one of the boundaries of your distillation. Then the other boundary on both sides happens to be the residue curve that goes through the feed. So now you can tell, just with a residue curve diagram, you can tell what are, with a given feed, you can tell what are possible residue compositions, and you can tell what are possible distillate compositions. Powerful. All right, so we're going to move on now. Just to have a look at some of the other possibilities when you have azeotropes. So let's have a look at this system. A, B, C, and A and B have an azeotrope called D, but also C and B have an azeotrope called E. Now, when you give the boiling points, let's have a look at this. That one's got a boiling point 409. This one's got a lower boiling point. So this is more volatile, and therefore arrows from E to B, E is more volatile than B because it's got a lower boiling point. Oh, yes, I am using pointer. E has got is more volatile than B, so the arrow will move from E to B, and the arrow also moves away from E towards C. Over here, we look at between A and B, this azeotrope, 389. And that is a lower boiling point than this one, and a lower boiling point than that one. So therefore the arrow is going from D to A, and also away from D to B. Right, now let's have a look at this azeotrope boiling point. Is a lower boiling point than E. So the residue, because this is the more volatile azeotrope than E, you will get a residue curve with a direction going from D towards E. Okay, and now you can fill in the only missing arrow, and that is from A to C. A is more volatile than C, so the arrows will go in that direction. Now, once you've got those, you can see you will have a boundary going from D to E, and the only way you can fill in the residue curves, this area here looks very much like the area that we had before, where this is A, B, C in order of volatility, most volatile, least volatile. And so you can see that the shape of these residue curves in this area DEB looks very similar to a standard residue curve diagram that we've looked at before. And so over here we can still add if we've got a feed that looks something like this, we can still do exactly the same thing about figuring out what are the possible distillate and bottoms regions. But the most important point here is that you can't distill out of this region. There's a sort of triangle, this region I'm outlining here. That region, if you start with a composition that's inside that region, you can't use distillation to get a composition that's anywhere outside that region. I'm going to start drawing lines again. There is the unstable node, assuming that let me draw the line. There's that's the unstable node. Assume that the feed is over here, and you can get an EB composition that looks like that on the other side. Oh, I'm not using the pointer. Now we're going to draw a line from the stable node through the same feed, but the best we can do is to get to that boundary over there. We can't go beyond that boundary. So we are making pure B, the least volatile component of these three, considering that this azeotrope we can consider as a component. We can make pure B, and then we will make that azeotrope. We can go no further in the distillation, because this thing that separates D and E is a distillation boundary. Okay. We're almost at the end of the lecture. In the same way, you can choose, let's choose a feed that has a composition. Oh, gee, no, I didn't mean to do that. Let me clear. A feed that has the composition let me show you where it is. That composition, a feed with that composition, you can take the unstable node and draw a line through it, and on the other side of the distillation column, the mass balance will give you AC at that composition. Now we can also take from the stable node, and I'll draw the line from there through the same feed. There we go. So if we have a distillation column that makes pure C, the least volatile component, then we're going to make something that has the composition represented. Oops, I need the pointer. That'll make the composition there on the distillate side of the distillation column. Okay, clearly that's going to be the bottoms because it's the least volatile. That will be the distillate. For this column, represented by the other red line, this will be the distillate, and that will be the bottoms because of the direction all of the arrows are pointing. Arrows always point to the least volatile component. Okay, so even though these residue curves on this side look fairly strange, this is again the only way of linking these arrows that you first make on the boundaries. There's another boundary arrow, there's another boundary arrow. If you want to fill this space with residue curves, there's pretty much only one way of doing it, and that's pretty much what's shown. And once you've drawn all of the residue curves in and you've got a given feed, you can immediately see what is possible as a distillate, and the other side, the bottoms of that column, or a distillate there, and the other side of that column, the bottoms of that column would look like C. So, enough to take in for a day. And we'll carry on with this tomorrow morning then. Any questions before we go? Yeah, still going to have chances to write mass balance tests. Yes. As far as I could see, there were only 9 students who have not shown that they're capable of mass balance tests, and I will be scheduling that. I'll let those 9 know by an independent email. I'll send it to each of you individually, and then you'll have a chance to write the mass balance test at some stage. How will the semester test mark? Let me switch off recording in the meantime.